attending any conference, it's incredibly important to be there. That's kind of the only way to really dedicate your time to be there and kind of be immersed in the whole thing and not distracted by other stuff going on, even if you do get distracted with interesting conversations in the hallway.
Okay, so hello everyone. Thank you for coming to my second ever CppCon talk. So it's good to be back. So I'm Daniel. I'm a teaching faculty member at CMU. I teach large undergraduate algorithms classes, and in my spare time, if I have any, I like to work on C++ libraries for parallel computing and parallel algorithms. So today we're going to be talking about atomic shared pointers. So brief rundown of what we're going to learn today. So we'll get to see a bit about how shared pointer is implemented under the hood. We'll hopefully see a lot of atomics and various concurrency patterns. We'll see how existing lock-free atomic shared pointers are implemented. So in particular, we'll talk about the so-called split reference count technique, which is sort of the state-of-the-art technique currently for doing lock-free atomic shared pointers. And we'll talk a little bit about deferred reclamation, which is essentially garbage collection in C++, and we'll see how we can use that to implement what I think are simpler atomic shared pointers in C++. Now, I want to keep this talk as accessible as possible, but given that it is a fairly tricky topic, I'll have some baseline assumptions. So hopefully you've heard of lock-free programming before, and you have some vague idea of what a compare exchange is. Similarly, you've heard of atomic, right? And you know how to use $ostd atomic. You don't have to be an expert, but you know roughly what an atomic is. And you've heard of shared pointer. So in other words, you just walked into a talk on lock-free atomic shared pointers. I'm going to assume you know what those words mean as a baseline, but not too much more. And we won't cover some of the bells and whistles like alias pointers and weak pointers. Those are interesting, but kind of orthogonal to the things we want to talk about. So we'll mostly sweep those under the rug for now. So why is this important? Okay, why are you here? Well, I've already got you here, but actually Bjarne did a really good job of sort of introducing this point for me in his keynote yesterday. So the NSA has recently come out with some guidelines on using memory-safe programming languages. So in particular, right, they say that we recommend the use of memory-safe languages when possible. And this includes languages like C#, Go, Java, Ruby, Rust, and Swift. For some reason, C++, they forgot to put that on their list somewhere. So, this is not great news for us, but, there is something we can do. So they do say that, okay, the use of added protections to non-memory safe languages, okay, they're not perfect, they don't provide complete protection, but they do provide considerable protection. Atomic shared pointers are precisely one example of an added protection for memory safety to a non-memory safe language. So that is what we're going to be talking about today, and that's why I think that we should be talking about this kind of topic today. So we want to talk about lock-free atomic shared pointers. So a quick rundown of what is lock-free. Well, approximately, and a good enough definition for this talk, is that lock-free approximately means don't use locks. Who'd have thought? Now the tricky part is technically that's not a 100% accurate definition. There are algorithms called lock-free locks, and there are also algorithms you can implement that don't obviously take a lock anywhere but are not lock-free. But 99% of the time, lock-free means don't use locks, and that's good enough for this talk. So a little bit more formally, in case you're interested, essentially in a lock-free algorithm, we have the guarantee that over time, at least one thread will make progress on its operation regardless of scheduling. So one way I like to think about this, actually, my preferred intuitive way of thinking about lock-free is that if a thread is scheduled and it tries to make progress and it fails, it must be because another thread made progress instead. So you can only be blocked from making progress because someone else made progress. You cannot be blocked from making progress by someone who is also not making any progress. So that's the way I like to think of it. Okay, so we want to talk about lock-free atomic shared pointers, so let's refresh. What is a shared pointer and roughly how does it work? So a shared pointer, okay, a shared pointer of type T holds a pointer to an object of type T. There it is. Okay, what else does it do for us? Well, in order to facilitate memory management, it has this thing called a control block. So it points off to this control block on the heap, and this control block contains an atomic reference count, right? That is a counter that tells you how many shared pointers are currently pointing to that same T object, okay? So it's 1, because there's one of them. So if we now make a copy of the shared pointer, we are going to get a pointer to that same managed object, that same T, and a pointer to the same control block, and we will have now incremented the reference count to 2 because there is 2 of them. Okay, and that is done automatically for you. Now, if we get rid of the first shared pointer, like maybe it goes out of scope or we point it to something else, the reference count will automatically drop down to 1. And if we get rid of the second shared pointer, the reference count will go to 0, and now, automatically, with no intervention from the user, the managed object will be destroyed and the control block will be deleted. So that is the memory safety that we are looking for, right? We don't have to remember to delete the object ourselves. We can't accidentally delete it twice, right? We are free from the bugs of memory safety because it's done for us, okay? So then what is atomic shared pointer? Like, what can that shared pointer not do? Okay? So atomic shared pointers, I like to say, were invented to answer this age-old question. Is shared pointer, if you Google this is an actual screenshot, this is not photoshopped, is shared pointer thread safe? And is shared pointer atomic? Another great question. Is shared pointer slow? Unfortunately, also a common question. So is shared pointer thread safe? Okay, well, I don't trust Google, I don't trust random people on the internet, so let's think about this ourselves instead. So I have 2 threads that have a shared pointer pointing at the same managed object T. So the reference count is 2. So let's say thread 2 says, I'd like to make another copy of that shared pointer. That's going to bump the reference count to 3. Thread 1 says, I don't need my copy anymore. I'm going to get rid of it. That's going to drop the reference count to 2. Thread 2, I don't need my S2 anymore. I'm going to get rid of that. Drops the reference count to 1. Okay, and that was all safe. The reference count is atomic, remember? So that was thread safe. No bad things yet. Now, thread 2 says, I actually want to reassign S3 to point to something else. I'm going to point it to some other thing. So now the reference count of that current T object is 0, because no one's pointing anymore. And now, thread 3 comes along and says, I'd like a copy of the shared pointer. I'd like to know what this T thing is you're dealing with. And now we have a problem, because thread 2 just decremented the reference count to 0, which is now says automatically, I've got to delete that object, okay? So it gets deleted. And thread 3 is in the process of getting its own copy of the shared pointer, which is now pointing to a deleted object. And so we have ourselves a use after free. So this is not so good. So is shared pointer thread safe? The answer is no, okay? The reference count is thread safe, but the shared pointer itself is no more thread safe than anything else. And this surely shouldn't be that surprising because it's no more thread safe than an int, right? If I just had an int and one thread was writing to it and one was reading, that would be a data race, okay? So shared pointer is no more thread safe than any other non-synchronized variable, okay? So to solve this problem, we have invented atomic shared pointers, which were added to the C++ standard in C++20. So an atomic shared pointer has the main API of atomic that we've known to come and love. You can store a desired shared pointer in it. You can load the current shared pointer and get a copy of it. Or you can do a compare exchange, right? And if you've forgotten what compare exchange is, quick refresher. Compare exchange is just if the current value is what I think it is, then please write the value I want. Otherwise, tell me what the current value actually is. And that happens atomically. Okay, this is like the bread and butter of lock-free programming is compare exchange, okay? So that is atomic shared pointer, and these are now thread safe. So if you use these, your threads no longer catch fire. You can load and store at the same time. Okay, so what is it good for? Like, okay, what can we actually implement now that we have an atomic shared pointer? So if I were to ask you, how many lines of code do you think it takes to implement a lock-free, memory-safe stack? Sounds kind of hard, right? I mean, lock-free programming is hard, right? I mean, you can go to whole CppCon talks that are just about implementing a simple lock-free data structure that go for an hour. Well, I claim that if we have atomic shared pointer at our disposal, you get a lock-free, memory-safe stack in about 10 lines of code that fits on a slide. And this is not slide code. This is real C++. You can copy-paste that into any C++20 compiler, and it works today. And it's great, right? This is a lock-free, memory-safe, it's ABA-proof, it's linearizable, it's all the adjectives you could ever want. It is a great lock-free stack implementation in like 10 lines of code. It's wonderful, okay? Well, there is just one problem. Is it actually a lock-free stack? I don't see any locks in here. So by our definition, I don't take a lock. It must be lock-free, right? But is it lock-free? Well, kind of depends, right? Is our atomic shared pointer lock-free? We have an abstraction. Maybe it's hiding a lock from us. Well, we can go and look, right? So I said these were added to C++20. So let's go and look. What do we have? So as of now, GCC and Microsoft STL have an atomic shared pointer in their standard library that you can go and use today. libc++ does not have one as of when I checked a few days ago. So both of them have an atomic shared pointer that you can use. Are they lock-free? Unfortunately, no. Neither of them are lock-free today. So you might think, well, that's disappointing, right? Like, why are they not lock-free? So why? Like, we want a lock-free atomic shared pointer, don't we? Is it just not possible? Is it too hard? Well, yeah, kind of the answer is it's hard. It is really, really hard to implement a lock-free atomic shared pointer. And let's see why. Okay, what is fundamentally the problem? Like, what goes wrong if you try and implement an atomic shared pointer? So we have an atomic shared pointer. It points to a control block that has the ref count and some other things. So what goes wrong? Let's say we have two threads doing, two simple operations, one a load, one a store. It's about as simple as you can get. Okay, so thread 1, it wants to load the object, which means, okay, I have to increment that reference count. Thread 2, I want to store a new object, which means I need to decrement the reference count because I'm getting rid of that object and replacing it with something else. And what happens if the decrement happens first? So let's break this down. I call this the race to zero. So thread 1 says, I would like to load, please, so I load the control block pointer. And now thread 1, it's tired or it's hungry, so it goes to the sports bar to grab some lunch. And while it's out, thread 2 comes along and says, okay, I want to do my store. So I'm going to take the desired control block, I'm going to exchange it into the atomic control block, and the thing that I get out, that's what used to be there. So I have to decrement the reference count of what used to be there, since it's not there anymore. If that decrement zeroes the reference count, shared pointer says, okay, it's my job to clean that up. So I'm going to destroy the managed object, and I'm going to delete the control block. Thread 1 now comes back happy from its lunch break and says, okay, I want to copy, I need to increment. And that is a use after free because the control block was just deleted by thread 2. And that is fundamentally the difficult part of implementing a lock-free atomic shared pointer, is you need to avoid that use after free that happens when you race the reference count to 0. So somehow, fundamentally, if we want a lock-free atomic shared pointer, we need a way to ensure that that control block is not deleted before we increment the reference count. And that's much easier said than done. So what solutions do we have at our disposal? Well, solution 1 that we know of is locking. Okay, let's just say we take a lock. And this is what is used by libstd C++ and MSVC. Thankfully, even though they are taking a lock, okay, they didn't pack a mutex into the atomic shared pointer. That would be even worse. Thankfully, they do at least do a very, very efficient locking strategy. So they actually use the 2 lowest order bits of the control block pointer. So you basically use the low order bit as a spin lock. You just try and set that to 1, and that means I've got it. And if you spin for too long, you can sort of do a back-off strategy where you use the second bit and go to sleep, and then the thread that holds it will wake you up when they see the second bit. Okay, so we're using the 2 low-order bits of the control block as a lock. Okay, so better than packing a mutex and actually increasing the size of the atomic shared pointer. So with that, okay, the algorithm becomes fairly straightforward. You just do the algorithm, the naive algorithm, but you put a lock around it. So to load, you take a lock, you increment the reference count, and you return a shared pointer. And to store, you take the lock, you exchange in the control block that you want, you decrement the ref count of the old control block that used to be there, and you're happy. Okay, you had that lock, which means that you don't have the use after free because you don't have a race. But not very satisfying if you if you're working with many threads and the lock-based solution ends up being too slow for you. So, can we actually do a lock-free atomic shared pointer? If you've been at CppCon last year, you'll have seen a talk by Timo, who actually said, yes, you can do a lock-free atomic shared pointer, and here's a rundown of that. And he talked about the split reference count technique. And I'm not going to assume that you've seen his talk, so I'm going to run down the split reference count technique as well. Also, because I think it's one of my favorite concurrent algorithms. It's really cool, so I want to tell you about it, even if some of you may have seen it before. So this is pretty much the state-of-the-art lock-free atomic shared pointer algorithm. It is used in production. It's used in Folly, Facebook's open source library, used in production. It's also used in Anthony Williams' commercial concurrency support library called Just Threads. Anthony Williams also has a free version on GitHub. It's not exactly the same code, but it's roughly the same algorithm, just sort of simplified a little bit. And there are other implementations you can find floating around. There's like hobby projects on GitHub and all of that. So how does it work? Like what's the key idea? Well, the key idea is that if we could somehow magically load the control block pointer and increment the reference count at the same time atomically, we'd be good, right? We would avoid the race to zero. And I mean, that's what you get sort of for free by locking, but we want to do it lock-free. So if you could magically do this, and I say magically because this doesn't necessarily sound like something we can do, if you could do that, everything would be good in the world. So how does it work, or what's the idea? Well, the desire, right? This desire is kind of like, okay, we want to do this load control block and increment the ref count somehow atomically. But this sounds like too much to hope for because of two reasons, at least. One is that the control block pointer, well, that's in the atomic. The reference count is over in the control block. These are two different memory locations that aren't next to each other. How can we atomically read and modify two different memory locations? Well, no hardware today pretty much supports an operation like that, so that sounds a bit far-fetched. It's even worse than that, actually, in that you don't even know where the ref count is until you've loaded the control block, because it's in the control block. So there's also a data dependency between knowing like where the ref count even is before you can think to increment it. You have to load the control block first anyway. So atomically doing these two steps, like directly as written, seems like too much to hope for, seems unrealistic. So what if we can somehow do something similar instead? We can't increment that reference count atomically. Too hard. What if we had a different reference count that we could increment atomically? What if we stick in a second layer of reference counting on the atomic shared pointer itself? So this is kind of the big brain idea of the split reference count technique, is we are going to protect our reference count with a reference count. So the reference count is protecting the managed object, and then the reference count is protected by another reference count. There's two layers of reference counting now, not just one. So if I was born sooner and I got to invent this, I would have actually called this two-layer reference counting. I like that name better than split reference count. I think it's more intuitive, but I was born too late, so it's called the split reference count technique. But the big idea is that we are going to use a second layer of reference counting local to the atomic shared pointer to protect the other reference count so that we don't get that use after free. Okay? So how we do this, right, is we take our control block pointer and we pack it together in a struct with a local reference count, okay? So that's the second layer of reference counting that we're putting in the atomic. Okay, so now if we put these two together in a single atomic, now we can atomically do stuff to that, right? We can atomically read and modify the reference count at the same time because they're in a single atomic. Right, so this key idea is that this local reference count is going to count essentially the number of in-flight load operations that are currently happening on that pointer. Okay, so this reference count tells us how many loads are currently happening, and then the global ref count is just the normal reference count that tells us how many shared pointers we have. Okay, so that's the big idea, a second layer of reference counting that tells us how many in-flight loads there are. So how do we implement this? Okay, well, our goal would be to write code that looks roughly like this. And some disclaimer, this is slide code. You can't, some of this may not literally be copy-pastable. Think of this as pseudocode in the style of C++. This isn't all 100% legitimate compilable code, just for the purpose of fitting it onto a slide. So the goal is we'd like to be able to write a load that looks like this. It looks kind of like the locking version of load, except instead of protecting with a lock, we want to protect it with this local reference count. So we want to implement some kind of magic increment local ref count function that will increment the local ref count and read the control block. Then once we have that, we know we are protected. Now we can increment the global ref count, make our shared pointer, and now we're done and we're happy. Now we can decrement the local ref count and be on our way. So if we can increment these two magic functions, we will have what we want. So increment local ref count, if you've done any lock-free programming before, is pretty much a stock standard compare exchange loop, right? We are going to take the current counted control block with the control block and the ref count. We're going to increment the ref count by 1 and try and install that into the atomic shared pointer with a compare exchange. If we fail because someone else has done something first, we just try again. And we keep looping until we successfully install an increased reference count, okay? Once we're done, it means we've incremented the reference count and we've got a copy of the control block pointer, which is safe, once we've implemented the rest of the algorithm at least. So slightly trickier part is how do we decrement? Well, the first half of decrement is kind of the same and it's roughly what you'd expect. Another compare exchange loop, okay? We take the previous control block with the ref count and we decrement the counter and we try to install it back with a compare exchange again. If we fail, we try again. But there's an extra case here that we have to be a little bit careful of. Because what if we notice when we fail the compare exchange that actually the control block pointer has changed? Like we failed the compare exchange not because someone else modified the ref count, that's okay. If we fail because someone else modified the control block, that means this atomic shared pointer is now pointing at something completely different. And so we can't decrement the local ref count of that because that's a ref count of a different object. I'm not allowed to decrement that one. We need to decrement the ref count of the object that we actually read. So then we're going to have some backup case to handle when this happens, okay? So this is essentially what happens if a store comes in and stores a completely different shared pointer over the top of you while you're doing your load. You come back and you find the control block is completely different. So like what actually happens there? So we have to figure out what to put in this mystery branch here, and we'll fill that in a moment. We'll figure out what to put there once we see the store operation. Then it should become clear what has to go there. So there's a mystery branch that we're going to fill in. Okay, so if we want to implement store now. So here's our regular vanilla store, like without any protection, right? We just take the desired control block, exchange it in, decrement the ref count of the old one, and then we're good. But that decrement right there, okay, that's the race to 0. If we just do that decrement willy-nilly and we hit 0, the in-flight loads are dead, right? They're all dead. So somehow we have to do something to protect them. So the store operation, okay, is going to heroically come in and save those loads from use after free. It's going to save them from the segfault. So the store operation is going to look at the local ref count that it just got out of that counted control block. If it's not 0, it goes, oh, there are some some loads in progress. I need to help them. I need to protect them or I'm going to kill them. So I'm going to take their local ref count and I'm going to protect them by sending that onto the global ref count on their behalf. Okay, so I'm going to take the local ref count and just add that onto the global ref count inside the control block. This means that any in-flight loads are now guaranteed to be safe because their ref count has now been added by at least 1 for each load. So the ref count can't be 0 now, okay? Because we've taken their local ref count and we've put it on the global. So by doing so, we've now guaranteed that those loads are safe and protected from the use after free. Then, once we've done that, now we can go and do our decrement and everyone is happy. Okay, so this is really the big idea here is this helping step, right? We see those in-flight loads. We're like, I don't want to kill those. I want them to be safe. we protect them by looking at their local ref count and sending that onto the global ref count. Right? That keeps those in-flight loads safe and protected. This is like the big step of the algorithm here. Okay, so now that we've seen that, now we can figure out what to put in our mystery branch, right? So now we go back to our decrement local ref count. So this is remember, this is the final step of the load operation. So the load has incremented the local ref count, taken a copy, it's incremented the global, and now it's ready to just clean up. So the decrement tries to lower the local ref count in the CAS loop, but it discovers now that a store must have taken place. Someone has changed the control block completely. Well, if that's happened, if a store has changed the control block completely, then that means that store is going to add its local ref count onto the global ref count. So that local ref count we were trying to decrement, we know where to find it now. It's not there anymore. It's now on the global ref count. It's been added to the global ref count on our behalf to protect us. So if we find ourselves in this scenario, we simply fix it by decrementing the global ref count, right? Because if we're in this branch, it means that a store increments the global ref count on our behalf. And so we just decrement it now to restore balance and order to the world. Okay? And that is the split ref count algorithm right there. Okay? So the question now on your mind is, okay, cool, like pseudocode and everything, how do we actually implement that? Like, how do we make this work? So there's probably at least one question on your mind, right? At least one thing you're suspicious of. I've got this atomic struct with a counter and a control block pointer, and you're like, hang on, that's 16 bytes, like at least, right? Like that's not an 8-byte thing. Can I put that in an atomic? Like, will that even work? Or will that just take a lock? Or will it not compile with some weird linker message? Well, there are two ways you can get around this. One, you can assume that yes, you do have 16-byte atomics available on your machine. And apparently this is actually an argument, but I mean, I'm in the camp of, okay, most modern machines, pretty much every modern CPU has 16-byte atomic operations. So if you are on a machine where you know that is true, which is most CPUs built in the last 15 years, then you can go ahead and use a 16-byte atomic. Unfortunately, STD atomic, even if your hardware supports it, STD atomic might not want to omit the 16-byte instructions, somewhat because of ABI backwards compatibility reasons. So one way you can get around this is actually use boost atomic. I got this from someone actually commented on Timur's blog. So Timur wrote a blog post complaining about this. Why can't I use 16-byte atomics even though my hardware supports them? And a friendly commenter said, use boost atomic, it works. So that's the workaround. If you use boost atomic, it will try to pretty much always use a 16-byte atomic if it's available on your hardware. And this is basically the technique used by Anthony Williams' library. Okay? He assumes the hardware has a 16-byte atomic, and so it will use that. Okay, what if you're in the camp where you say, no, I really don't like 16-byte atomics, they don't exist, or maybe you agree they exist, but you don't like that they're slower, right? They're about twice as slow as an 8-byte atomic on x86, because it's twice as many bytes, who'd have thought. So, some people like avoiding them just because they are slower. So your other option, and this is what is used by Folly's implementation, used in production, is instead you try to pack your pointer and your local ref count into 8 bytes. So you get 48 bits of pointer and 16 bits of local ref count. And this will work on x86, right, for the foreseeable future, because your virtual address space is only 48 bits worth of pointers. So you're guaranteed for now that those 16 extra bits are usable to you, right? They're not going to be used. So this works on x86, may not be portable to other platforms though. And this gives you 16 bits of counter, which essentially means you can have 2 to the 16 threads doing a load at the same time, which is probably enough for most applications. You can either just assume that's always true, or if you want to be safe, you can do what Folly does, and actually they have a test where they check, okay, if the local ref count's actually going to go like above how many bits I have, then I just spin lock as a backup. But that's like never going to actually happen most of the time, because who has 60,000 threads, right? But you can guard against that if you really want to. Okay, so that is the split ref count technique used by Anthony Williams' implementation with the double word compare exchange, and by Folly using the pointer packing trick. Is that the only way to implement a split reference? Is that the only way to implement an atomic shared pointer? Well, it seems like to many people, yes, that is the only way we know of how to implement an atomic shared pointer. Okay, if you went to Timo's talk last year at CppCon, he talked all about this. This is sort of the folklore algorithm that people know about for doing atomic shared pointers. But I claim that, no, it's not the only way. There is another way you can do it. And surprisingly, I'm a little bit surprised that at least I haven't seen publicly anybody else try this idea, because in my opinion, it's actually much simpler. It's much simpler than that quite complicated split reference count algorithm that we just saw. Maybe some people have thought of this, right? And they've got it hidden away in their secret production code in their company, and it's not open source. So I wouldn't be surprised if other people have thought of this, but it appears that it's, broadly speaking, not general knowledge. Like, this isn't at least shared around on the internet or in open source anywhere. So here's a different idea. So let's first quickly review, okay, what was the problem we were trying to navigate around, right? It's the race to zero, as I call it. So you want to do a load. You load from the control block, the load thread goes and gets lunch, the store comes along and says, okay, I'm going to exchange in my new control block, decrement the old reference count, that might hit 0, now it gets destroyed, and so thread 1 comes back from lunch and does a use after free, because that control block is now gone. So fundamentally, the problem we need to solve is that we need to guarantee that after we've read that control block, that it is not deleted until we've finished reading it. Now, if you've done a lot of lock-free programming before, if you're a lock-free programming expert, I claim that this should kind of scream a technique at you, right? This is a textbook technique of deferred reclamation. I want to read something, and I would like the guarantee, other threads, don't delete this from me, please. I'm reading it, and then I'll tell you when I'm done, and then you can delete it. Right? This is a textbook use case for deferred reclamation technique. So a quick primer on that in case you are not an expert in that area. So what is deferred reclamation? Well, at a high level, we have some atomic source object, okay? So it's holding some heap allocated T, and multiple threads would like to read from it and swap it for different things. The threads that read from it would like the guarantee that they can read from it without it being deleted out from under them, because they don't want to use after free. But the threads that are storing to it and changing the value don't want their things to leak. They also want the guarantee that stuff will get deleted once it's not used anymore, right? Because you could just solve the problem by never freeing anything, but that's not a particularly scalable solution. So the interface that deferred reclamation tries to support is we want this magical protect operation. So protect says, I would like to read what's in this atomic source, and I would like the library to promise me that while I'm reading it, no one deletes it. Okay, I need to be able to read it safely without anyone freeing it on me. Okay, so once you're done reading it, you can imagine releasing the object, which just says I'm done with it, I don't need this anymore. Now in modern C++, because we like modern C++, so in modern libraries for doing this kind of thing, we don't typically explicitly call release. We'll wrap that in a nice RAII guard somewhere, right? So we'll have some nice RAII type where we can protect from the source, and then when we drop that guard on the floor and it goes out of scope, it will call release for us so we don't leak. So usually we've wrapped that behind RAII, and then the other magic function that we need is this retire function. So retire is essentially the equivalent of delete when you're doing deferred reclamation. Retire says, I'd like to indicate that this object has been removed from the source, it's no longer visible to the world, therefore I'm ready for it to be deleted. But someone might still be reading it. Someone other than me might still be reading it and have it protected. So please delay the delete until everyone who is reading it is done. So retire P is essentially a synonym for delete P once no one's reading it anymore. Okay? And then, of course, one way to implement this trivially would be never delete anything, just leak. So that's not very scalable though. So usually most techniques involve something like, occasionally, say every 1,000 retires or so, go through the list of the stuff you've retired, and if it's not protected, you can delete it, right? So you basically just accumulate up a pile of garbage and periodically you go and clean it up, okay? You just clean it up if it's not protected. Otherwise, if it's protected, you keep it and you don't clean it up until next time, okay? So that's deferred reclamation. And the common implementations of this fall under like two main categories, and there's a ton of variants of them, but these are like the two high-level ones, hazard pointers and RCU, or read, copy, update. And a cool thing for us is that these are, in the concurrency TS, perhaps on their way to C++26. We don't know for sure yet, but there's a chance that they'll come into C++26, and I hope they do. So if we're lucky, we'll get those in C++26. That'd be really good. For now, you can implement your own. So there is an implementation of these in Folly. I have my own implementations. So for now, you can roll your own versions of these, and they're very useful. Okay, so armed with deferred reclamation, right? We have this powerful technique. What can I do with it? So let's try and use that to implement an atomic shared pointer now. Okay, so here is one way that we might try to do that. Let's take our load method, looks pretty similar to before, but now instead of just reading from the control block, which might be freed at any moment, we've got no way to protect it, instead let's read it using hazard pointers, right? Let's use deferred reclamation. So we'll grab ourselves a hazard pointer guard, right? That's the clever RAII type that will release for us. So we'll grab ourselves a hazard pointer, and then we will protect the control block. So we're telling the hazard pointer library, please promise me you're not going to delete this thing. I'm reading it. And then, now that we're pretty sure that it's protected, we'll increment the ref count and return our shared pointer. And then RAII will kick in and it will release the protection for us. Okay, so question for you all, see if you've been paying attention. So does this prevent the use after free on the control block? Who thinks it does? Who thinks it does? Anyone? I sure hope so. So who thinks it doesn't? Or who has an opinion neither way? Okay. So if hazard pointers aren't lying to us, yes, this prevents the use after free on the control block, right? That's what it's designed to do. Hazard pointers tells us, I promise you, you protect this. I'm not going to delete it until after you're done with it. So it does prevent the use after free on the control block. But is the code correct? Who thinks this code is correct? Who thinks this code is incorrect? Okay, who shout out an idea why? Why might this code not be correct?
Release is missing.
The release. So the release, I'm assuming, is going to happen automatically from the RAII type, right? Like this hazard pointer type will like release the protection for me. So I'm okay with the release like being there hidden in the RAII type. There's a more subtle problem here. I've guaranteed you that the control block is not freed. Only the control block. What if an in-flight store is still racing with us, they decrement the ref count to 0, and they say, okay, ref count 0, time to destroy the managed object T. It's still totally possible that the reference count may have been decremented to 0, which is going to cause the managed object T to be destroyed. The control block is safe. We protected the control block, but only the control block. So we don't get a use after free, but when we hand this shared pointer back to the user, they get a use after free because now they're accessing a T object that was destroyed. And we've essentially just resurrected a zombie object, right? We've taken the ref count, which was 0, and incremented it back to 1. So we've given the impression that this object is alive and well when it was actually already destroyed. So we've really just offloaded the use after free from us onto the user. So we didn't quite get this right. So how can we improve this and make it better? Well, we can instead try the following. Here's a proposed fix instead. Instead of just protecting and then incrementing, we are going to protect and then increment if not 0. We're going to add this other funny operation. So we're going to have to do this in a loop because it might fail. We are going to grab ourselves a hazard pointer. We are going to protect the control block. I'm going to say, I need that control block to not be deleted, please. Then we will try to increment if not 0. If that succeeds, we've incremented the ref count, and we're promised by the library that ref count wasn't 0. And then we can return the shared pointer. Everyone's happy, there's no zombie objects because the reference count wasn't 0. If we fail though, we might fail this because the ref count actually was 0. And so increment if not 0 fails, returns false. Then we just have to try again. Okay, we have to try, okay, let's see what the new control block is, because that indicates that someone stored over the top of this, put a new object there and decremented the ref count. So if we fail to increment if not 0, we simply loop and try again. Now you might be wondering, okay, but now we need this another magical function called increment if not 0, right? We need to keep going further. I claim that we don't have to do any work here. I claim that if you have a standards conforming shared pointer today, it already has this function. It's already there. Anyone want to shout out, why is that function definitely already there?
Because the ref count is atomic.
The ref count is what, sorry?
Atomic.
Because it's atomic, well, the atomic doesn't necessarily have a function called increment if not 0. We can implement it ourselves, but I claim that it's already in your shared pointer. It's in your standard library shared pointer for sure. Weak pointer, yeah, it's got to be there because it's what weak pointer uses, okay? Weak pointers hold on to a control block, but they don't hold a reference count. Instead, when you want to upgrade a weak pointer to a shared pointer, you try to increment the reference count. If it succeeds, you return a shared pointer. If it fails, you return a null shared pointer, or you throw a bad weak pointer exception. So this function is already in your standard library, okay? If you have a standards conforming shared pointer and you have weak pointers, then this increment if not 0 is already there. This function already has to be there for shared pointer to exist in the first place. So we don't even have to implement that function ourselves. Now, if you did want to implement it yourselves, it's not too bad. It is just another compare exchange loop, right? Where you just read the counter. If it's not 0, you try and compare exchange +1. If it fails, you try again. So it's not terribly bad to implement yourself, but it's already there. So I don't even have to do that, right? We're just piggybacking off existing features that are already in shared pointer, which I really like, okay? So that's our load operation. What about store? So here's a store implementation. Doesn't that just look like the normal store? That's the original vanilla store. There's nothing different in there, right? We just exchanged the new control block, decrement the ref count. We didn't do anything. Yeah, that's actually just the original store implementation. So what actually changed? Well, turns out we don't have to change store at all. What we do have to do is change decrement ref count. So we've got to go under the hood a little bit into the shared pointer. So when we want to decrement the reference count, okay, so a decrement ref count implementation will look something like this, okay? Ignoring some bells and whistles like the weak reference count and the possibility of custom allocators. I'm sweeping those under the rug because they're pretty orthogonal to the algorithm here. But otherwise, right, a decrement ref count in your standard library today will look like this. Okay, you fetch sub 1 off the ref count. You then check, did I 0 the ref count? Okay, so if this returns 1, because fetch sub and fetch add, they return the old value, not the new value. So if the old value is 1 and we subtracted 1, we just set the reference count to 0. So if that happens, we delete the managed object, and this is usually done through this virtual function called dispose. The reason that has to be virtual is because this control block might actually have a T that was created via make shared, or it could have been created via a new by the user and passed in. So this has to be virtual just to handle the different possibilities of where T actually is. Right? But assuming that function just deletes the managed object for us, right? We delete the managed object and then we delete the control block. Okay? So that is what a decrement ref count in your standard library today will look like. Okay, we need to change this up a little bit, right? Because if we decrement the ref count and then we delete the control block, that's our possible use after free on an in-flight load. So we go back to our deferred reclamation toolbox and we say, oh, someone could have this protected. We're not supposed to delete it. Instead, we are supposed to retire it. So we take our control block and we send it off to the garbage collector of hazard pointers, right? We send it off and we say, look, delete this control block, but hold off for a minute in case someone's still reading it. Okay, so then that control block won't be freed while someone is still loading from it. Okay, and there's our load operation again, just same one back from the previous slide. And that's the whole algorithm. And the reason that I really like this algorithm, think it's very simple and elegant, is because it fits on a slide, right? Unlike the split reference count, which is a multiple slide algorithm, even if you take creative liberties with your pseudocode, this whole thing pretty much fits on a slide. Okay, it's just a few lines for store, a few lines for load, and then just putting the word retire instead of delete in your control block, and that's it. Okay, so I really like this algorithm just because of how simple and elegant it is. Now, of course, I guess I'm cheating a bit because you need hazard pointers, so like there is a lot of code there. If you're using an existing hazard pointer library, well then this is good, this is free. Otherwise, you will have to roll your own hazard pointers. Okay, and then it's a few extra 100 lines of code to roll your own hazard pointers. But that's a thing that you can find, in existing libraries, and if we're lucky, coming soon to the C++ standard library. Okay, so that's the algorithm. Now this is CppCon, so of course you're going to ask me, okay, what about the performance? Okay, it's simple, it's elegant, but like, does it actually work well? Like, do I ever want to use this? So we are going to do some benchmarking. Now this is a talk about concurrent algorithms. Benchmarking concurrent algorithms is really hard. It's not easy at all. There are so many factors we have to consider. We have to consider, okay, throughput versus latency. We have to consider different workloads, like what if it's mostly reading, like just mostly loading from the shared pointer, or what if there's a lot of writes, a lot of stores or compare exchanges. One that's commonly forgotten about, but one that's actually super important, especially for multi-threaded code, is hotness. Am I benchmarking my data structure when it's in cache already versus when it's not in cache? Okay, this is a part that a lot of people they don't realize that they should do this, right? It's very important to consider like the performance difference of your data structure, whether you're loading it hot or loading it cold, right? Because they will perform very differently. And of course, we're multi-threaded code, so we have to consider contention. It's probably going to be way faster to load from an atomic shared pointer that no one else is touching versus one that 100 other threads are trying to store into. So we also have to consider different contention. So to do this thoroughly would require hundreds of benchmarks, and I have 5 minutes. So I'm just going to show you a small set of benchmarks that I think give you a good idea of what's going on and show you some of the trade-offs. And hopefully this is useful and interesting enough. So I really like that concurrent stack that I showed you at the very start, the 10-line stack. So for our benchmarks, we're going to benchmark that. Okay, we are going to implement that concurrent stack, but to compare the different atomic shared pointers, we are just going to swap the atomic shared pointer for different implementations of it. So we're going to use mine, we're going to use Folly's, Anthony Williams, and the one from the standard library and see what happens. So for the benchmark setup, how do we actually control all those factors I just told you about? Well, we're going to have p different threads, and we're going to vary p from low to many, and that's going to help us control the contention and the throughput, right? More threads is going to mean like more contention, right? More threads accessing the same stuff. And hopefully more threads means like more throughput, at least subject to contention, right? Those are kind of related. We're not necessarily going to get more throughput if we get more contention, but if we can get less contention, we might get more throughput. We're then also going to vary the number of stacks we actually use. So we're going to have n stacks. So we could have just one stack, and every thread just goes at that same one, or we could have many stacks, and the threads go at different ones, and therefore this is going to like lower the contention, and depending on how many stacks, this will allow us to control the hotness. If I have just a few stacks, they're always in my cache. If I have 1,000,000 stacks, most of them are not in my cache, and to load from them is going to measure like the out of cache throughput that I can get. So we are going to then, one final parameter, we're going to do u% pushes and pops, and the rest are going to be peaks, right, where we just look at what's on the stack. So 100 minus u% of the operations are essentially read-only. We're just reading the stack. The others are going to modify it, and that's going to control like the workload. So we're going to basically vary these 3 numbers to get a decent cross-section of all these different parameters. So our benchmark loop is essentially going to be this, right? We have p threads, and all of them are doing this. With u% probability, we want to do an update. We are going to pop from a random stack 1 to n, push to a different random stack. Well, it might not be different with some probability. It could be the same stack. And otherwise, we're just going to peak at a random stack. Okay, so we expect that the read operation, just peaking, should hopefully be much faster and better throughput than the pushing and popping, which is actually a lot more contentious. It's doing a lot more updates. And we're going to benchmark this on our benchmarking machine. This is a 4-socket Xeon. It's got 4 18-core CPUs, so 72 CPUs. It's got a terabyte of RAM, Ubuntu 20, GCC 13, all that good stuff. Okay, and I'm actually really lucky because GCC 13 like only just became available on Ubuntu 20 like in the last week or something. Like before this, I couldn't even do it on this machine because the OS was too old to install GCC 13, so I was so happy. Good timing, very good timing with that. So first benchmark, n equals 1, so we've just got a single stack. So that means really high contention. Every thread is banging on the same stack, but it's hot in cache. One stack definitely fits in your cache. It's not very big. So I'm going to benchmark these 4 algorithms. We're going to do libstd C++, right? That's the GCC one that just does a lock on the low bits of the pointer. I'm going to do Anthony Williams' free version of his library from GitHub, not the commercial one. We're going to do Folly's open source implementation, and we're going to do my one that uses hazard pointers. I'm going to see how they work. So we're going to vary how many updates we do. We're going to vary that U parameter. So here's 1% update. So this means the workload is mostly reads. We're mostly 99% of the time just peeking at the stack, and only 1% of the time are we pushing and popping. And you can see that in this case, okay, the throughput is looking really good for my hazard pointer implementation, right? It's about twice as fast throughput as Folly, right? Once you're using more than a few threads, right? They're much more similar up there at 1 thread, but once you've got a lot of threads, this actually really starts to take off. Okay, what if we start to do more writes? Okay, well now they sort of squeeze together a bit, right? If we do 10% pushes and pops, this graph's a little hard to read, so I'm gonna delete the p=1 experiment just to zoom the graph in a bit so we can actually read it. So now what we can see, okay, once you start doing a lot of writes, okay, the writes really kind of dominate, the throughput goes down a lot, and now we see that the hazard pointer one and the Folly one are pretty much neck and neck, and the libstd C++ and Anthony Williams one are neck and neck, but a bit lower, or a lot lower. Okay, now we can say, okay, let's take it even further, 50% updates. Okay, well now I definitely need to delete the p=1 experiment to read this graph, so let me do that. Once again, actually pretty similar to the 10% one, we've got Folly and the hazard pointer one pretty neck and neck, and then we have the libstd C++ with the lock and Anthony Williams one neck and neck, but a lot lower. Okay, so this is the high contention hot in cache benchmark. Let's now go to n=10. So now we've got moderate contention, right? Like the threads are going to be picking a random stack from 1 to 10. So there's a decent chance they hit the same one, but there's a decent chance that they don't. So there's going to be quite a bit less contention, but n=10 is still a small number, so they're still hot in the cache. Okay, these are still always in my cache. So now if I do 1% updates, again, we can see that in this case, the hazard pointer one actually is doing really well. Okay, it's pulling ahead nicely. Folly's doing pretty good as well. The lock is not doing very well at all. That's sitting right at the bottom. Then we go to 10% updates, and we kind of start to see a similar pattern again, right? Once we start to do a lot of updates, the implementations start to differ less in their performance, and that's because updates are really the bottleneck, right? They're most of the work, and they're harder to actually optimize. So again, sort of neck and neck with Folly here. And again, 50% updates, same idea, right? Hazard pointers and Folly, pretty neck and neck. Anthony Williams and libstd C++, neck and neck, a bit lower. Okay, so I've shown you benchmarks where the hazard pointer one is better. I have to be fair to Folly now. Now I have to give you a benchmark where Folly actually does better. Okay, n=10⁶. I've got 1,000,000 stacks. So this is really low contention. It's very unlikely 2 threads are going to pick the same stack at any given moment. And you're out of cache, right? It's very unlikely that you're going to hit the same stack as the last few that you just hit. So it's most of the time you're hitting a stack that is cold for you and is not in your cache. So now we're actually going to see a different pattern here. So now all of them actually scale pretty well, right? Even the lock-based one, because hey, there's like no contention. So now the lock-based one is actually doing pretty good because it almost never has to compete for that lock with anyone else. But Folly pulls ahead even just a little bit more, which is pretty nice. In fact, Folly's scaling is like really good here. Hazard pointer one is just a bit behind, right? It's competing with the others. And the double word CAS one of Anthony Williams is a tiny bit slower because the double word CAS takes a bit longer than the single word compare exchange. Okay, we can go to 10%, and once again, pretty similar. Folly is still winning, still ahead, and the others are pretty close right behind. And then we can go to 50% updates, again, Folly staying nice and good, even when it's cold in cache. So sort of take-home message here from these benchmarks is that Folly's implementation is actually really good when your stack is not in cache, okay? It loads out of cache really, really well. But when everything is hot in cache, the hazard pointer implementation seems to have a pretty big advantage. So there's no clear winner here, right? It does depend on the workload, and that's why it's important to benchmark various different workloads, right? That's, in particular, this is why I said it's very important and often forgotten about that you should benchmark your data structures in and out of cache. If I didn't think to do that, it would just look like mine is always better, and that would be unfair to Folly, which does really well when you're loading cold in the cache. Okay, so those are my benchmarks. Obviously, for a complete picture, we would have to do hundreds more, but I think that provides a nice, decent, cross-section of the performance profiles we get under various measures here. Okay, so that's the main stuff that I have for you today. So you can find my implementation. It is on GitHub, so you can go and look at my atomic shared pointer up there if you want. It's still a proof of concept, but it's reasonably featureful. I still don't have atomic weak pointer, and I still haven't done alias pointers. I'm still deciding. I want a way of implementing alias pointers that have zero overhead to the non-aliased case, and the trade-offs there are a bit annoying, right? It's a bit annoying to get alias pointers that don't slow down the rest of your code when you're not using them. The way Folly does it is they just add an extra layer of indirection, which succeeds in not adding overhead to the non-aliased case, but then it makes some people mad because you're allocating stuff. So I'm still trying to figure out if there's like a best of both worlds way to get the best there. And there's some interesting avenues of future work we could look at. Like, is there some nice hybrid algorithm that somehow gets the best of both? Like, can we write an atomic shared pointer that is the best when it's hot in cache and cold in cache, right? I have some ideas that I'm thinking about that I'm going to try, and we'll see what happens, but I haven't done that yet. And it would also be interesting to look at latency. So I only had time in my talk to talk about throughput, but if you're interested in latency, I do have some preliminary results that are on my GitHub and that I've run some measurements for, and you can always come talk to me about that. So optimizing latency is a next sort of step to looking at this technique. So thank you very much for coming, and I'm happy to take any questions you have.
Hi, thanks a lot. Very good talk. Could you go to the slide with the deferred reclamation?
Which slide,
code?
sorry?
The deferred reclamation code, where you call the retire operation. Yeah, so I wonder, does the dispose of operation need to be deferred as well? And also, does the dispose also deal with custom deleters and stuff?
Right, so the question was, what about dispose? Could or should we defer the dispose as well? And what about custom deleters? So, okay, custom deleters is the easy one. That's why dispose is virtual. So if you have a custom deleter, this will call an overload that calls the custom deleter. So that's all handled. Actually, really interesting point, what if we defer dispose as well? Actually, so I gave a CPP talk last year where I talked about essentially wrapping hazard pointers and RCU in smart pointers. And that's exactly what they do. So if you want to think about what if I just defer the dispose as well, you should watch my last year's talk on YouTube, because actually it is exactly that algorithm where we defer more stuff. All right, so this algorithm in particular, we don't actually defer the dispose. And the reason is because then we wouldn't truly have the API of an atomic shared pointer, which says when you destroy the last copy, I want the ref count to hit 0, and I want my object to be destroyed immediately. Okay, so for an atomic shared pointer, the user sort of expects that when I take away the last copy, synchronously in the current thread right now, my object should be destroyed. They might be relying on that fact because maybe they have a recursive data structure like a linked list, and so they need the destruction to happen immediately. So for an atomic shared pointer, we don't want to defer the dispose, but it is a totally cool but different algorithm if you do want to think about deferring more stuff. And that's my CppCon talk from last year. So go watch that if you want to see that idea play out. Another question.
Hey, yeah, so on this same slide, it seems like if you try to load and the reference count is already 0, you're just opting to hang instead of potentially dereferencing something you don't want to dereference.
So the question is, so if we fail to increment here because it's 0, what was the point? We're going to stall here?
Yeah, you're in the while true.
Well, we're in a loop here, yes, but we are going to just try again, right? So in other words, this algorithm is not wait-free. It does not guarantee that every thread gets to load in constant time or bounded time. It is a lock-free load, which means it can get starved. but it can only be starved if there's a lot of writes clobbering it, which means other operations are succeeding. So it still meets the definition of lock-free. It's a very interesting question. Can you implement a wait-free atomic shared pointer? Yeah. And that's another thing that I have some ideas in my head that I want to try, but I haven't done it yet. So I hope we can also get a wait-free atomic shared pointer one day, but I haven't done it yet. Okay. But I'm going to try.
Thank you.
Hey, thank you for the interesting presentation. It was a nice build-up to get to actually see how it works in the hazard pointer. So I actually have two questions. The first is just really want to clarify my understanding of how retire works. And basically the way I understand the way you described is it's going to defer the destruction, which means that it's no longer deterministic when it's actually going to call the destructor. And in this case, it's okay because the control block doesn't really do anything significant as part of its destructor. Is that correct?
Yeah, that's the main idea. So the comment was like we're deferring deleting the control block, which means there is non-determinism. But this actually relates very well to the first question where, you know, if we defer deleting the object, that's like very non-deterministic now because there could be recursive destructors that we don't know what to do with. But your comment was very accurate, which is that deferring the destruction of the control block is sort of less non-deterministic because the control block doesn't have super fancy behavior in it. It's unless you have a really, really weird custom allocator in it, it's trivial, in fact, because it's just a reference count. So in fact, deleting the control block, if you don't have a weird custom allocator with a weird destructor, is a trivial operation and does nothing. So it's non-deterministic, but there shouldn't be any hard-to-predict non-deterministic side effects unless you do something really weird with a non-deterministic custom allocator.
Great, thanks for confirming that. The other question I had was more around the benchmarking, and you said you couldn't put everything on the slides, which is understandable, but I was wondering if within your own experiments you found any other situations where you saw that the hazard pointer implementation isn't really winning the race there.
Okay, I think I'm out of time, so let's talk about this more
sure.
later.
No worries.
Cool. Thank you.